Thank you for coming for this session. It's almost the end of the second day. I think not many of us survived and came for the session, so I really appreciate that you came here. Let me ask this question. How many of you not .NET developers here? So all the .NET developers? Two .NET developers. OK, that's fine. I find that it's always good to ask. Sometimes people just want to see how it goes. And maybe they can apply some of the things not in .NET world, which is totally fine. This is totally legit excuse to be here. So my name is Viktor Gamov. I work as a developer advocate at a company called Confluent. Any of you heard about Confluent before? A few of you. OK. So apart from making awesome T-shirts, Confluent is also contributing a lot to Apache Kafka. And we also have our own distribution of Apache Kafka. We kind of like ship it in the cloud. We ship it everywhere in the world. I'm going to be showing some of the Kafka running on Kubernetes today. And also, we do support Kafka clients ecosystem. As one of the clients that is actively used and actively used in the community is the .NET client, which is based on client that's written in C. It's called Liberty Kafka, and this client is a foundation for many other clients, for Go, for Python, and many others. So welcome to the session. A few words about myself. I build highly scalable Hello World applications. This is probably we'll try to do today. This is something like that. Also, this is also important slide because you can find my Twitter handler. It also will be important for the demo. Hopefully, if you have a Twitter here, we will be able to participate in some of the demo. And if you didn't catch my Twitter handle, it is conveniently placed on every slides. So don't hesitate to tweet if you see something interesting to tweet about. I would like to, before I'm jumping into like full .NET API breakdown and things like that, I would like you to brief about like why Kafka was built, why we continue to contribute, why we think it's an important piece of modern data infrastructure, and a couple words how the Kafka came into play. So first of all, when you look at any enterprise these days, you can see that when you exchange some information, you're building some of the like business processes, workflows, and so far and so on. You are building the workflow, data flows. But when you're trying to model these systems into software, usually building some sort of like a data store. Like can be a three-tier application that has a database, some business logic, and some front end that user will interact. And not much of the data flows here. So in the pre-streaming world, the organizations, they typically build this kind of small silos for particular departments. They might be doing some of the things with some SaaS providers, some of the data warehouse, some of the other applications. They might be, if it's small applications, they might communicate to each other through like database. They share schema and things like that. Some other departments, they're doing similar things. And things are getting more interesting when you need to start exchanging this information between multiple systems. You need to exchange information between one department and another. And usually it comes into what we call the spaghetti architecture. So essentially, instead of just getting some like direct access to some systems, we start getting access to a database to fetch some data. Not every system exposes API. So this is why they're very popular these days. A lot of program products like API gateways, where you can like hide some of the complexity behind API gateways, but they're not solving overall the problem of the spaghetti architecture. And another problem is these days is the monolithical applications, because it's very difficult to think about this, it's very difficult to talk about them, they're very difficult to modify, and usually you need to have someone who knows everything about the system in order to explain how the data comes into play. And if you're in a big organization and you're running some of the different like big data tools or like data processing tools, there's someone who can explain this, how the data flows in the organization, which is not cool. So this is why the LinkedIn, the Kafka came into play almost like 10 years ago, I guess, already. they try to solve the problem how they will remove some of the repetitive data and enable different teams to effectively communicate. So at the time, there was no such word as event streaming platform. So they come up with this idea, this log-based data system, which is essentially file. When you're writing at the end of the file, you're reading from the beginning of the file, so that's why it looks like a messaging system. So, but it also provides some of the abilities to persist data, store data for long term, and so far and so on. Over the time, this thing evolved into what we call event-driven system. Apache Kafka is an event-driven platform that includes not only this like pops up thing, but also include multiple introduced components that we're going to be talking about today. So in this data streaming world, the way how the system they communicate via this medium that's called event streaming platform. And the different data pipelines, including some big data tools, including enterprise tools, everything, they communicate through this centralized system. That doesn't do much, you might say. It just provides the way how your data will not disappear, how data will not be lost. So it provides you scalability in order to withhold a large amount of data. If you have multiple producers and consumers of this data, you need to have a system that will be able to perform very well under loads. And these days, it starts very actively used to break down the monolithical applications and become a kind of sort of source of truth for exchanging data of your applications. With the event streaming platform, many organizations enabled more real-time use cases. And combining with some of the historical data, they enabled what we called contextual event-driven applications. So you can combine real-time aspect of like data streams that come to the system, plus joining with some historical data that allows you to have enriched result. So in the stream processing world or data processing world, this is how the things look from the 10,000 feet, I would say. We have a massive number of systems or applications that produce data, and we have this like highly scalable platform to perform high throughput operations. Now, in general, because Kafka is written in Java, and it basically came into like JVM world. Technically, it started as written in Scala, but right now the Java is quite okay to continue to contribute. So less and less Scala, more and more Java. And now the how we can do stream processing, usually like all like cool kids in Java world, they have it all. But KSQL, this is something that we develop at Confluent to provide the stream processing for masses, so the people can use this without knowing of underlying components, without knowing anything about Java and how it will be run. And the serving layer will allow us to not only do processing of this data using tools or like language like SQL, but also provide the way how this data can be queried by the system who don't know anything about Kafka at all. So this is something that we're going to be talking about. So 3 things that I want to focus today in this particular talk, and to explain you event streaming platform as a new type of software, new type of the data system. I'm going to focus on about storage, the way how storage works and the way how data is stored, the way how the clients can access this data using pops-up pattern, and how they reading data, the concept of consumer groups, how data is consumed, so far and so on. And we touch base a little bit on the processing, and probably we'll run some demo. We'll see if we have enough Twitter accounts in this room. Sometimes people just, we don't know this Twitter thing, so hopefully it will be engaging. Now, let's start with first thing. So first thing is storage. So usually when I talk to people, I ask if they know the Kafka, and people usually say, oh, that's some sort of like a messaging system. Like, how many of you have the same perception? Right, not many. At least few who honest about this. The rest of them just probably tired or shy. Kafka, as a matter of fact, has more in common with distributed database than with the messaging system. So from the messaging system's design of the Kafka inherited this like a pops-up pattern. But the way how the data is stored, the way how the data distribute across multiple nodes in order to provide the fault tolerance and provide this ability to survive after certain failures, it actually came from many the existing like databases or like databases that came in the era of NoSQL. And so that's why I would like to talk a little bit about storage. So when we're talking about data systems, we need to establish some sort of like a core abstraction that we're going to be operating on, right? So like when we're talking about databases, usually it's a table that defines how we structure our data. If we're talking about more complex system like Hadoop, for example, or HDFS, because it depends, HDFS is a storage for Hadoop and its foundational core abstraction is a file. But in terms of Kafka, what do you think is a core abstraction here? I will give you a hint. Log. Who said log? Okay, so you probably can get a T-shirt. It's some. I have a few more T-shirts, so you need to pay attention so you can win some of the T-shirt. Correct. Log is a fundamental data structure that we use in Kafka. As a matter of fact, as a data engineer or software engineer, there's only probably 2 data structures that you need to know in your life. Yeah, probably 2 or maybe even 3. So probably you need to know how hash map works and how the hashing in general helps to figure out the data distribution. Probably you need to know something about bit tree, because this is the most frequently question asked of software engineer would enter the country, and the customs and border patrol officer will ask you, if you're a programmer, can you explain how you can walk through bit tree? And not only this, but also B3 used in the database indexes. So if you're trying to figure out how databases are doing search and stuff like that, they're using B3 as a data structure. And log is a third data structure that you need to know. So hopefully I will help you to learn something about this. And it is actually a very simple data structure. It's a file. Imagine file where you're just writing data into the end of the file and reading from the beginning of the file. This is log. Very simple, or the word log itself might be overused over time because we're using log to describe application like history. But you think about this, you also, if you're writing some log files, you're also writing in the end of the file. You're reading from a beginning of the file if you need to read this, or even you tail it, but when you tail it, you're reading from certain position until the end of the file. Another similarity of this like application log is that all these messages that placed in log are immutable. So you're not changing anything in this once it's written. So it is immutable and you're not changing it. Unless you're trying to change your application log, maybe you're doing something fishy, you're trying to hide some of the secrets that you did in the application. Otherwise, you're not changing logs. So now to the pops-up pattern of accessing the data. All the messages in Kafka, when we are pushing data into Kafka, reading data into Kafka, actually have two things. They have a key and value. So key value, this is what one particular thing will include. Also, there's some of the additional information. Maybe there's some headers that were added later in the game that allows to do ship some of the metadata with actual data. It might include some information about timestamp and offset. We're going to be talking about offset in a minute. Now, this is how write operations happens. Again, writing to the end of the file or reading from beginning of the file. The way how we consuming this data is a little bit interesting, because if you ever use any messaging system, you're kind of expecting that when you consume this data, you acknowledge that you consume, this message will disappear. Well, this is not the case with Kafka, because Kafka actually has very similar pattern of accessing the data, similar to the way how you're reading regular physical book. How many of you read physical book recently? Okay, so we understand what the book is. So you're reading book, going the page to page, and when you stop reading the book, you're putting some bookmark. So the next time when you're ready to return to reading this book, you find this bookmark, and after that you continue from the same position. So this is why how the Kafka knows where particular consumer is stopped consuming data. So this bookmark in Kafka world called offset, and when the consumer reading some message and processing this message and need to send acknowledgement that, okay, so I'm done reading, it actually increments this offset. Offset stored on the Kafka side. So if a consumer don't need to like store anything, when it connects with the same name saying, hey, I'm Viktor, and Kafka say, hey, you just stopped on the page 35, so here's your offset, you continue from this point. You can always throw away your bookmark and say, hey, I want to start from the beginning because I start reading this and I don't understand some of the things about this book, so I'm starting from the beginning. If I want to extend this, this metaphor to messaging system, for example, with the traditional messaging system, when you read your book, you're actually tearing down your pages. This is how it looks like. When you read the message and there is someone was late in the game, they have to start reading from some position in this book for like page 10 or 20, or depends on how far you went to tear down all these pages. So this is the huge difference between traditional messaging systems. So next thing is that these consumers also grouped into a certain group, and we'll talk about this in a moment. But the key, why a message needs to key, it's also very important. If you ever look into the way how the modern NoSQL databases work, probably heard term consistent hashing algorithm. This is where hashing comes into play. This is why I said it's an important data structure, or important concept that you need to understand. So based on the key, we're applying hash function, and based on this result of this hash function, we get some number that we divided by number of partitions. Partitions is just the buckets where your data will land. And this partition is distributed across multiple nodes. And this is how the Kafka and all distributed systems doing distributed systems job, how the data is distributed. In order to not rely on some third-party system that will be managing the discovery or the service discovery or certain nodes or certain data, producer and the server and consumer, they agree that this hashing algorithm would be consistent. They will have the same hashing algorithm, so this is why they will have the same result every time when we try to get the data for a particular key. Why it is important? Because just based on the calculating this quick hash function, you always know where the data is placed. This is why hashing or like a hash map or hash-based data structures are very fast to access regardless of the size of the system, because only time you're spending is to calculate hash function. It will be and after that you will land into the place where data will be placed. If you didn't put the key, it's fine. Kafka will also forgive you for that. In this case, message will be kind of like spread across multiple partitions inside the topic. So it's kind of, if you don't know the key or you don't want to provide a key, it's also fine. Kafka will take care of distributing data across multiple partitions. Now, as I mentioned a little bit earlier, we might have different consumers that might have different speed of processing, and it's totally fine. How many of you were like in the situation when you had a call from your operations person and saying, hey, your messaging queue actually like piling up some of the messages, looks like your application is not like performing well or things like that. There are situations like that, but with Kafka, data is persistent, data is there. So it's good that you have data. And only thing that will be changing is offset of particular application. So in this particular case, I have Ricardo, Robin, and Viktor, the consumers of this data. They're reading this in a different speed. Why they're reading a different speed? Because they might be doing something different. One of these, the consumers might have different algorithm of processing the data. For example, if we take in back this example with a book, like English is the second language for me, so that's why I'm reading book with the vocabulary. So I need to go and look up certain words in this vocabulary. So in this case, my processing time would be slower because I am doing enrichment of my stream with some of the historical data that was available as a kind of in the lookup fashion. Some other people might be interested in doing something else. For example, if I'm reading a book with my son reading the book much faster than me, simply because he doesn't care about letters. He cares about pictures. He's trying to find more pictures. So his algorithm is different from my algorithm for processing this data. So this is why they move with different speed. And you can track this position difference between the current position, for example, between this position and new data that comes into the system that we call the consumer lag. So how far we are from the high watermark of this topic. Very important aspect that even though you have a key value in your message, you never do kind of like a random access. Kafka is terrible to be a random access system. Kafka is fast because it has access through sequential reads and sequential writes. Though it's possible to reset or like jump to a particular offset, there is an ability to translate certain timestamp into offset or offset to particular timestamp. So you can navigate through this log. But it will be extremely slow if you're trying to do this like similar to some sort of like a distributed cache or some of the key value database. So don't do that. It's a read-only system. If you need to perform like lookups, like key value lookups and things like that, you need to offload this to another system or using some things that I will talk about this a little bit later in a few more slides. Now, let's talk a little bit about birds. It's probably one of the important slides to explain concept. Very difficult concept explaining with this beautiful slide. Concept of consumer groups. This is something that you not see in the different the messaging systems because they were created for different purposes. Now, Kafka is designed to be very heavy on reads. So this is why I'm bringing all this, the metaphors from the book world and the Kafka named after Franz Kafka, who was the author. He's writing very depressing books, which also reminds the way how you manage Kafka, if you manage Kafka yourself, if you're not using cloud, for example, or things like that. I'm just kidding. It's getting better. It's getting better. It's not that depressing. Now, in a Kafka, the way how you consume the data through consumer groups. So if you look on this picture, you will see nest. So nest is define a consumer group. And also you can see in this nest, I have 3 baby birds right now. So it is 3 consumers that's sitting in the same consumer group. So what does it mean? When I said the Kafka topics contains partitions, which is the way how the data is distributed, these small files that distributed across multiple nodes. So the responsibility for assigning this partition to particular consumers will be handled to this mommy bird, also known as consumer group coordinator. So consumer group coordinator, it's a part of the broker, and it knows like I have a topic, I have a 10 partition in this topic, I have a consumer group with 3 consumers, so I will distribute these topics among them. So this guy will get a 3, this guy will get a 3, this guy will get a 4. So now you have one topic that will be consumed in the 3 different consumers. If you want to have scale your reads, increase the speed how you consume it for a particular topic, you bring in more consumers in the consumer group. So these consumers, if new consumer will hatch, new baby bird will appear. Oh. If you didn't get the idea of partitions, these worms that mommy bird will feed these baby birds is actually partitions. So he will get 3 worms, 3 and 4. And the mommy will be responsible for balance this and equally distribute this food. If we have a 4, we have one more baby bird hatched. Now, mommy bird will stop feeding process, will distribute these partitions again. So it will say you will get 3, you will get 4, you will get no, it's going to be 3, 3, and 1, for example, because we increase number of consumers. So in this case, we increase the rate how we will consuming this data, because like one consumer can consume data, like two consumers can consume data from topic faster than one consumer. And if baby bird will fall out of nest, meaning that it will left the consumer group, in this case, mommy bird will stop feeding and will remove all these partitions from the current baby birds and redistribute them again. So this is very powerful concept just because it allows you to very granularly scale your reads. It also allows you to define the way how this data will land on certain consumers. If we're talking about some stream processing tools that we're going to be showing, with the number of partitions, we defining the level of parallelism, how this stream processing tools will be using data. Now get back from the initial geographics to the pictures that architects and engineers will understand better. So we have a topic that has 4 partitions, and when I start my application, my consumer application, it always has one consumer group. Consumer and consumer group. So in the case, all partitions will be assigned to this consumer group. If I want to read more data faster, and I can scale the consumer group, but starting multiple others applications, that will have same consumer group ID. So this guy's consumer group controller will be responsible for adding particular consumer to consumer group, and also rebalance this data. And as you already know, these two consumer groups, they actually can perform with a different speed because they might perform different type of operations. If failure will happen, right now we have a 1-to-1 ratio to like each consumer will be assigned to particular partitions. If one of the consumer will go down, one of the consumers will assume a responsibility of another one. Question to the audience, again, T-shirt here. What's going to happen if I have, in this particular situation, have a topic with 4 partitions, if I have a 5 consumers in consumer group? What's going to happen? What's again? Exactly, yes, it's going to starve. In this case, if you remember this, situation where we have a baby birds, so if mommy bird doesn't have enough worms for 11 baby birds, one of the baby bird will starve. It doesn't mean it will die. It will just do nothing, so it will be idling. So it will be part of consumer group, but no partitions will be assigned. So in this case, if one of the consumers in consumer group will fail, this new consumer will take over, so everything will work. But in general, this is something to keep in mind. Sometimes when I'm talking to people and they're trying to build this like distributed computation system, and they see that by adding more consumers into play will not adding any benefits, they say, hey, what's going on here? Like, how many partitions do we have? Well, oh, we just started topic by default with one partition. So what do you expect? There would be no benefits if you're doing one partition per topic. So this is it. And all components of this distributed architecture, they kind of separate, and they don't depend on each other. So producers can produce, and they will not affect the consumer. So you might have a very high ratio of writes, but your consumers will not be affected. You will not be able to, you will not overwhelm them. And the consumers, they also don't need to think about things like a back pressure, so saying, hey, don't do that. If you ever done kind of overflow of your listeners in JMS, you know what I'm talking about. You need to figure out the ways how you can communicate your consumer to your message broker, saying that, okay, I'm not able to receive any messages right now because I'm processing. So typically we're talking about a thing called back pressure. One of the things that I also mentioned, that Kafka comes with this replication built in, meaning that some of the data is duplicated in other nodes in order to preserve this data. So we have a topic that might have 4 partitions. These partitions distributed across multiple nodes. And now we have also replication factor of 2. So we have a partition number 1 that has a replica on a node 2 and node 3, and similar to other partitions and topics. So topic number 1 has a partition number 2, and there's replicas are here as well. And the reason why they marked in the different color, it's first of all, they are leaders. There's only one leader in the particular inside the topic. There will be only one leader partition. And the Kafka, the consistency model in Kafka, the way it works this the way that all reads and all writes will land on leader. So it is not eventual consistency system. Like every time when the message will be committed in this log, consumer will see this immediately. There's some interesting things that we can deep dive into at how the consistency works. We can chat about this later. But in general, it's something to remember. Your reads and writes always happen to leader. Yes.
Each partition has the same data has the entire information for that topic. Right?
No, it just has its chunk. Data is partitioned by key, so it will have only data that will be applicable for a particular key because of the hash function that was applicable there. So it will be, you will have an out-of-the-box balancing of the data across these partitions.
So in that case, the order in which the messages are consumed is not the same order in which they came into the topic?
Wrong. This is a fundamental piece of Kafka. In order how data produced, it will be same order how data will be consumed from particular partition. Yes, we're not guarantee ordering across topic. We guarantee ordering across partition. But there's a case where you can have ordering across topic if your topic has one partition. So there's some legitimate use cases where it's possible. If one of these nodes will go down, one of the replicas will take responsibility of leader, and there's certain ways how we can ensure your durability of the data and make sure that when the replica will assume a leadership role, that data will be actual, not obsolete and things like that. There's different ways how we can configure acknowledgement on the producer. There's all 3 different types how the producer can acknowledge data. When the producer writes data into Kafka topic, it can get acknowledgement either from leader, or it can have acknowledgement from the set of replicas that we called in-sync replicas. The replication is asynchronous. Like you might have a replication factor by 3, but you still might have 2 in-sync replicas, meaning that third replica will be synchronized in the background asynchronously. All right. So log is a special type of durable messaging system that similar traditional messaging systems just in the pattern how the data will consume in the kind of pops up fashion, but has a better scalability. You can scale your cluster by adding more nodes. It has a built-in fault tolerance, the replication mechanism that I just described, and you can configure replication based on different topics and the importance of certain topic and in the importance of the data. And it has built-in storage, so you don't need to plug in some of the afterthought of the designing of a messaging system that, oh, now we need to have a durable messaging system. So should we bring some database and do maybe distributed transactions right into database and write to my messaging system? You don't need to do that because the storage piece is also built in. Sometimes people can say, oh, the Kafka is more like a messaging system with database durability guarantees. It's a stretch, but it's not far from truth. All right, so let's see some demo, shall we? So in this particular demo, I will be using some of the examples that we have in the repository. Where is it? In the repository that will be responsible for communicating with Kafka. So it's the Confluent Kafka.net. It's the it's on GitHub, it's open source, and if you will try to find some of the Kafka clients that available for .NET. You probably will find the .NET client from Microsoft from 0.8 of version of Kafka. And let's see, .NET Kafka. And you should be seeing something like not ours, like Microsoft. Let's do it. Yeah, so C# client for Kafka. If you will try to go here, you will find that it's actually, first of all, it's archived, it's read-only, and they actually recommend to use Confluent Kafka.net as a replacement. So we're going to be looking to this one. So this project is based on Liberty Kafka, which is a pure implementation in C. It has the bindings to C# and some other libraries. You can install it pretty much on any platform. I'm running Mac. I'm not running on Windows. We support .NET Core. We support .NET Framework, and it works fine in the server. There's no like a platform dependency or things like that. Works very well with customers who use Windows, and works well if you're using some of the cross-platform things. And as a matter of fact, some of our developers who develop this, they use Mac, and they use like VS Code just to develop this in the test on Windows on CI server. I want to show you a couple aspects here. So first of all, I'm going to be using this local installation of my Kafka. Let me see if I start. I'll do scheme registry. So I'm using this local installation of Confluent platform. We ship it with a set of tools that you don't need to kind of like think much about like what kind of tools you go to start, what kind of shell script you need to start, and so far and so on. So it knows in what sequence you need to run certain commands. So Kafka depends on Zookeeper. Zookeeper is another form of database that allows to store some of the metadata for Kafka. Kafka will be using like service itself, like it will start. And now also I will be using a thing called scheme registry. So when you're writing data into Kafka, Kafka really don't care what you're writing in it. So Kafka really handles any type of data. It can be binary, it can be files, it can be JSON, whatnot. So the way how it works, Kafka streams data from socket directly to file. So it doesn't deserialize this data, doesn't do anything with this data. So that's why it's just binary data will land on file. But as a developer, you care what kind of data you're putting there. Especially you care if you're trying to build some sort of like a microservice architecture and you have one team that writes data in .NET, another team uses data in Java, third team uses Go, and now they need to exchange the same information. They need to have some sort of contract. So to establish this contract, we have this open source tool called Scheme Registry. So essentially it's a REST service that allows to store some sort of schema for my data. So in my example, I want to show you here. So in this particular case, this schema looks like a JSON, but it's very hard to read over here. But what we actually do here is we have this object called user, and it has multiple properties like a name and favorite color. And now we also need to provide some sort of like a platform independent definition. Have you ever used the things like protobuf maybe in your life? So this is something that also independent of the platform. So you can use this between multiple systems, written in Java or written in Go, for example. Now, so what we're going to be doing this, we're going to be producing data from my .NET application. Data will land to Kafka. I will show you how I can use tools that don't know anything about what kind of language was at the producer side of things. So Kafka ships with lots of tools. And using the scheme registry, I will be able to extract the schema from this REST service and also display this data in my application console. I'm switching back here in my application, and I'm using .NET Run. So a couple things that I need to specify. So this application will connect to Kafka. So the first parameter, this is the port where my Kafka is running locally, because I just started this. I'm using scheme registry. Scheme registry, this is the Let me actually start Kafka topics. So I would like to show right now that everything is working, and because I'm using scheme registry itself uses Kafka to store data. So think about this, you can have a service that doesn't have any other dependencies except Kafka. So the way how I like to describe this and the way how I describe this is like French people say, we drink our own champagne, right? So we still using Kafka not only as a thing to read data from and write data to, but also we use this as a storage for some our internal stuff. Actually, I'm not sure if French people saying that, but I like how it sounds. It's better than it sounds like dog fooding or something like that. So that's why we actually use some of the Kafka topics to produce some of the metrics and store schemas here. So Kafka is up and running, so it can respond to my commands. Now let me run this .NET application. And now I define this topic with schemas. So this application, okay, because I entered different directory, Avro specific. And now I should be able to run this. So this application, the source code you can find in this the examples folder. All sorts of things here, just simple consumer, simple producer. There's example how we can work with Confluent Cloud. The way how the .NET team works in Confluent, they're trying to provide a most idiomatic ways how you can use certain APIs that might not necessarily written in the way how the .NET people expect this. So this is why there might be some of the lag between how the Liberty Kafka implements certain feature and how these things will appear in .NET Kafka. But usually team is very responsible, and on GitHub they also respond with some of the questions, and they're very cool people. And I have a luxury to work with the team, and they help me to prepare to this demo. Now, okay, so let's write some of the users. But before I do that, so I will show you some sort of a real-time aspect of this. So I do have another console tool that's part of Kafka distribution that allows me just simply to read this, read this topic. I'm specifying that where's my Bootstrap server, and it specifies a. Let's do some interesting thing before I will do that. So let's do this, and I will produce something first. Now I can do some users. I don't know. Any Lethal Weapon fans? You're the reference? Or maybe Die Hard fans? Christmas is coming, right? Isn't it the best Christmas movie ever? Like Lethal Weapon and the Die Hard? So now I wrote the data to my Kafka topic. Now when I'm trying to consume, and this is one of the confusion that people might have, they're saying, oh, I'm trying to consume, but I don't see any data. Am I missed something, or am I doing something wrong? So in this case, I need to do something like here. What was there? I don't know, like any Highlander fans. I love movies from 80s and 90s. So what just happened? Did I miss my previous things? So the way how default consumer in Kafka works, it uses this latest offset. So it starts from the beginning because it couldn't find any offset committed inside the Kafka. So this is why we started from the top of this log. But if we will do things like this, say from beginning, which is a shorthand for resetting offset and starting from the very beginning of the log, we will be able to consume of this data. And this is also a very powerful concept. So once data landed into Kafka, even though you were missing something before data was arriving, you still can replay this data. This is very powerful because sometimes you're writing your app that processing this data or reacting on this data, and you know, the thing called bug happens. You know, you just like mess up with some logic, and now you need to replay this. What you usually do with messaging system, you ask in to resend this message over this message bus, so you will be able to test it. You don't need to do this with Kafka. You're just resetting your offset and starting from the very beginning. Yeah, so now I can continue to push some data here. So I don't know, like, not very excited about new Terminator. I'm still a Terminator 1 fan. Terminator 1, the best Terminator. Yeah, because it was like the real robot, and it was like, he was not talking jokes, right? So he was just coming and killing people. He was terminating people. So, like everything went wrong after Terminator, I guess, 2. No, 2 is okay. 3 was total disaster, and they should have stopped. Though I don't hate Terminator Salvation, it's I consider this as a good movie, comparing to Genesis or whatever his name. So anyway. So I would highly recommend to look to these examples, play around with this, and get the feel how it works. So Kafka also has this the API that allows you to programmatically do something with your data. So for example, creating topics or change the replication factor, change the partitioning scheme. So the admin client is the special type of client, apart from consumer and producer, that can do certain operations with our Kafka broker. All right, quick demo. We'll get back to some of demo in a moment. Now, it's cool that we can produce data, read data, write data, but what about actual processing of this stuff? And this is where we're going into the land of stream processing or streaming, where we kind of have some sort of tool that dealing with data as it arrives. And this tool don't necessarily need to wait until the data will end. It will be constantly doing something with this data. One of the examples of the stream processing is detecting credit card fraud. Why credit card? Because when I'm talking about money, people usually pay attention. So that's why, like, financial use cases always work at the conference. People, oh, okay, so something about money. I need to hear about this. So here's an example. We do have a stream of events that contain authorization attempts in our application. So you go somewhere, you swipe the credit card, it generates the event. This event lands into Kafka. Now, based on these events or some sort of maybe pattern of these events, we need to decide if all these transactions that happen are legitimate and our users perform this well, or maybe not. So let's take a look how we can do that. So we have a source stream that will contain authorization attempts. In this particular case, this how we define where we want it to derive. And in order to have this stream that will be constantly running, there's two types of queries that you can define. Is the continuous query, where it will be running only during the session of this request, or persistent query that will be running in background and constantly doing something. So this is why we need to create stream. And this stream will be constantly updating with new data that arrive into authorization attempts. Now, things getting interesting when we need to do some sort of aggregation. You can say, Viktor, we did this kind of like a stream processing many times. We get the message, we introspect the message, and we continue to do something on this. This is what we call, like, when we do like a filtering or transformation of the message, that we call stateless stream processing. Because in order to calculate particular step of your operation, you don't need to know past. You don't need to know the previous step. So that's why filtering and transformation, it's fairly easy to do even with JMS, right? You don't need to know, you need to store intermediate step. But anytime when you're trying to do count, aggregation, some sort of summing, some sort of computation where you will require data from the past, you need to store it somewhere. You need to either store it maybe in some database because you want to have a durability. And now you go into a world where you need to write in multiple places because you need to read data from Kafka, write to this database, read from database because you need to read previous state in order to calculate current state. So complicates a lot of things. So the thing that I'm showing you, this KSQL thing, is actually comes with these capabilities to do stateful stream processing. And you, as a user, you don't need to focusing on how this will be handled. Spoiler alert, it uses Kafka to ensure that data will not disappear if one of the persistent node will die. So it's another thing how we use Kafka, not only as a source of data that we're pushing, but also as a tool that ensures a durability of our system. Now, where we figure out this, we're creating one consistent stream from authorization attempts. Now, we want to implement this algorithm, super sophisticated algorithm. If we detected a few authorization attempts for a particular credit card number within 5 minutes, so let's consider it as a possible fraud, and after that we will send notification to the system to another department that will figure out. So this is how we're building kind of like a small reactive system that reacts on the incoming transaction, and it will notify if data will be applicable for this. So window, it's another dimension how we can group this, because we defined a couple grouping components here. So card number, this is how we grouping our stream. And because we're interested in card number, we're also specifying the number of counts. Time window, it is the way how we can define this like a finite the piece of infinite data. And the windows, they have different semantics. In this particular case, it's tumbling window that will be jumping kind of, or tumble. If you imagine that we have a slice of 5 minutes with the timeline of minutes, it's kind of will be like this square will be tumbling from one place to another. Trying to visualize with my hands never works. But essentially, every 5 minutes, this window will advance. And after that, previous result will not be in our interest anymore. So we're going to be going to another 5-minute window. And also, this is a logic where we define saying, hey, so if the number of counts more than 3, then do that. Send or emit a new event in this possible fraud event. So why are we doing this? One of the reasons why I'm here, because not many of us Java developers, not many of us Scala developers, thank God, but there's a huge number of people who data engineers, and they want to stay data engineers. They want to continue to do things, but with the modern tools, with like stream processing tools and things like that. So this is why we like break this or put another level of abstraction on top of the stream processing tools that we have and build this KSQL engine. There's UI that allows you to communicate this Confluent platform that I showed. This command also comes with some nice UI that's available for free for development. You can do whatever you want. KSQL CLI that was going to be using right now in a few minutes. It has a REST interface. Sometimes, and especially in the world of non-Java clients, there is a need for using the same Kafka streams semantics, like a Java library semantics, but without actually running the Java code. So that's why in your .NET application or even JavaScript application, you can actually query this REST interface and submit query to REST endpoint, and you get continuous query with results back from Kafka. And there's also headless mode, where you kind of prepackage your stream processing application written in SQL, and you ship it with to KSQL server. So in this case, it will be running. It will be REST interface will be disabled. So in this case, no one will be able to connect and interactively doing something in production. So this is what options to interact with KSQL. What I like to say about the Kafka in general, it is kind of like a database that has a storage, but the query engine is actually outside of this database. Where you have a traditional relational database, you have your storage, which is also, spoiler alert, log, transaction log, and after that, a relational database management system will materialize this data that comes into this transaction log as a table, view, materialized view, what have you, right? Different thing with Kafka, where your storage is separated from your query engine. And the query engine can be different. So in this case, it can be JVM application, it can be .NET application, it can be Go application, it can be Python application, it can be KSQL, it can be Spark, Apache Spark, it can be Fling, and so far and so on. Now, let's see some KSQL stuff. So, a very, very interactive demo. So I already have my, let me show you quickly. Any Kubernetes fans? All right, so I already running my small Kubernetes cluster with some of the stuff that contains my Confluent platform. In this particular case, I'm running 4 nodes on my Kafka in the GCP, and I'm running my Zookeeper here. I'm running my schema registry, everything what I need. But I also need data from somewhere. And probably you know that we Russian people very love your American Twitter. So this is why we collect, or Facebook, because, you know, why not? You know, this is how we collude with the greatest nation in the election and stuff. We love your data. So this is why we bring this data here. So in Kafka world, remember when I was talking about this components that allow you to ingest data in and out without you coding? So we're using this connector approach. So I was looking to this place called Confluent Hub, which includes all sorts of connectors to different systems. It's a confluent.io/hub. And if I will go here and say, OK, so I want to use data from Twitter directly. And I see, oh, there's a few connectors. So in this particular, there's a Kafka Connect Twitter connector that allows me to connect to Twitter Firehose for particular keyword. In this case, I'm using SpringOne as my keyword, and allows me to read data from Twitter Firehose. Now, let me switch back. So now I got the data. Data already landed in Kafka. If I will do show topics. KSQL gives me this like interactive console that allows me to look inside the Kafka. As you can see, there's a bunch of different topics here. Again, it's an example of our, drinking our own champagne type of thing. We're using this control center, which is our UI tool, to store some of the data inside the Kafka. Plus, Connect itself, Kafka Connect, this is runtime for connectors, also uses Kafka to store some of the configuration information stored offset from the different systems. And now this is my Twitter topic where I'm running things. Also, I already have some streams here. So I have a streams. I have a stream here that describe Twitter. That already contains parsed information from this huge JSON that I'm getting from Twitter. So in this case, I can do stuff like select. For example, if you right now will go ahead with tweet with a hashtag SpringOne, and we'll include something in Kafka, like, oh, Viktor Gamov is doing awesome Kafka demo at the SpringOne. You should be able to see this message right now. And you see this says press Ctrl+C for interrupt. So in this case, it is continuous query. It will be running until I am press Ctrl+C. In order to, hey. Awesome. So you see, it actually works. The Twitter Firehose, I'm reading this. It's going through this massive, like I said, it's a highly scalable Hello World application. Uses like all possible tools to do simple things. I don't use typical Twitter clients. I use my Kafka cluster on Kubernetes to read my tweets. So we can quote me on that. Also, like sometimes like my audience is not very responsive, so that's why I'm doing whatever all Russian hackers do, just go in and creating a bunch of faking Twitter accounts and tweeting myself. So in this particular case, SpringOne is awesome, Apache, Kafka, NET is fire. I will show you how I can use emojis in my stream processing thing. So it goes into space, from space into cloud, and here. So you see emojis are working. Cool stuff. Now, when I stop this, and I will run this again, I will not be able to see anything because, again, I'm reading only from the current offset. But how I can do and how I can return back in time. So in this case, I can go here and say reset offset for particular session when I'm running here, and when I will run this, like say limit 5. So in this case, it will read messages from the beginning of this topic, and with the limit of 5 messages, and after that it will stop. It kind of sort of simulate a typical behavior with the traditional database system. So some of the output we got here, or we did not. Every time when I do smaller font or bigger font, my console usually messes up. So let me do this once again. I reset this, connect through this REST interface. I'm resetting offset, and let me see if I will be able to show you 5 responses from the past. So I was running this cluster for a couple days, so starting from Monday. So now you can see some of the messages that we just talked about appeared in my screen. Now I can change this say like everything. So in this case, I'll do limit 3 because people were tweeting a lot during this conversation. So it will just print only 3 events from my topic. Now you can also we can have this permanent. For example, this tweet, I would say create stream. Let's call it tweet about Kafka as select. So in this case, let me remove this this limit. So it will create a stream. It will not spit out any response, but I will be able to show streams, something like that. So this my tweets about Kafka is running. So all good, and things are awesome. Now I can perform certain aggregations. So I will just give you some examples. So I'm not going to be running this, or maybe we should running. So like if someone is tweeting about me, I can do this. Or let me actually create a persistent query for this guy. So in this case, where's my user with the account? So now I can create a table that will be counting all the tweets about my person during my presentation. This is what I usually do. Like I want to see, I'm very eager for people's attention, so this is why I'm doing this, and I'm seeking for like people to talking about me, whatever. So and I can do this with this query. It will be like my session goes for 1 hour. I can start this, and after that I can go and see how many people tweet about me. This is what you can do with tools like KSQL. Again, KSQL also complements the standard producer-consumer that you have, and doesn't really require you to do anything from perspective of like a programming. So this is where you're programming. So where you can go next. So there's a website .io/tutorials. Let me show you if you. So it is a website that we have like working examples for particular use case. You can grab those and you can execute yourself, and after that you can learn how to do certain complex things with very easy tooling. So in this particular case, like if you're interested in how to do simple filtering of the streams of events, you can go here, ignore all things about vanilla Kafka and Kafka streams, and look for KSQL. And do we have any like Docker fans? These demos are fully Dockerized, so in this case you don't need to run any crazy environment, so everything can be run on your laptop, so everything will be cool. So KSQL also supports like a producing data. So you can also insert into the stream. So in this case, you don't need to have a producer per se. KSQL supports ever schema in order to introspect the message, and because S in the SQL is for structured, so we need to have this structure in place. This is what you get if you need to have a filtering. So you're just doing something like this, right? So only books of George R.R. Martin, because the author is George R.R. Martin. So this is how you're writing, constantly running stream processing application just with just a few lines of code. Where we can go after this? So tutorials website, you have it. You can also grab some of the stream processing books. They somehow related to some of the Java aspects, though this book is more, again, more inspirational, because where the Jay Krabs is talking about why he wrote Kafka when he was in LinkedIn. But my personal favorite place is when I'm not doing the conference talks, I'm hang out in the Confluent community Slack. I'm sorry. This is where you can ask any type of questions. There's a Slack group for .NET clients as well. Or like there's all sorts of clients, and engineers from Confluent hang out there. So thank you very much for coming. I really appreciate that you stayed longer and not many of you left. I think I did something right here. And as always, I'm available for enhanced interrogation. Thank you so much. Any questions? I have a one t-shirt left, so. OK. I didn't hear the question, but hey. Good catch. Nice one. You can try. We still might have some of the t-shirts at the Confluent booth. What's the question? Oh, so the gentleman with t-shirt, you need to have a question in order to get this t-shirt. Otherwise, you have to pass it to the gentleman who will ask a question.
So when is your next session?
I'm done for today, and I'm literally leaving the venue and go straight to airport, because my next session probably will be in Melbourne, Australia, next Monday. So yes.
So is it the consumer's responsibility to remember where its bookmark is, or is this something that Kafka?
So the question was, I'm repeating this for audience we're recording, is it the responsibility of consumer to remember of this offset? So there's two answers to this question. So essentially, you have a control. So you know when you're done processing, you can manually commit offset. So in this case, it sounds like, OK, I'm done. This is manual acknowledge. Usually, clients, they have automatic acknowledge after a certain time, either timeout. So it's just a kind of notification or API call that you need to do. Offsets are stored inside Kafka. So there is a special topic that's, let me show you. If I'll do show topics, there should be topic called __ consumer offset. Why it doesn't show me everything? My console is broken. Yeah, but there's a special topic that stores inside the Kafka that's responsible for storing consumer offset. Kafka will, if you don't do anything, Kafka will make sure that this offset will be saved. Yes?
Performance impact building the stream topology with KSQL or programmatically?
So is there any performance impact building stream processing topologies using something like, I guess you mean that like a .NET client, like a plain .NET client?
Using KSQL or programmatically with Java or with
There will be no performance impact on Kafka, because only things that these two applications are doing, they're reading data from Kafka, and Kafka is highly optimized to be like very heavy on reads. So there would be not much of the performance. Only difference is that KSQL will be kind of generating this topology, and really depends on how complex your logic there. There's not so much optimization you can do. You should rely on the things what we do underneath if we're trying to optimize your query. When you're running this programmatically, you have a more control over the things what you can optimize. But in terms of performance, again, it's very weight question, because like what kind of number of performance, like how fast you consume this data, and your consumer lag would be like a lower, or like a number of messages of
Consumer processing the messages.
yeah. So usually they use like similar like high performance consumer libraries, so there should be no like visible differences, but it also will be dependent of like users code versus code written by this KSQL, the query parser and the topology builder. So I would say it really depends, but in general we recommend just like if you feel comfortable of running some of the part of your logic in KSQL, you can do that. If you feel that you need more flexibility in running stuff in some of the programmatically, you can do that, and they still can kind of coincidentally be part of the same pipelines. Yeah. They can be complementary. Yes.
What are the chances of any loss of data from the producer side?
So what are the chances of data loss on the producer side of things? So there are chances, as always. We optimized and we fixed a lot of things in the producer side of things to support, we call it like idempotent producer. It's also part of Libardi Kafka, and I believe it's also part of .NET Client as well. So there is a certain the fencing mechanism that's available on the broker side, where not allowed you produce duplicates, for example, in case of network glitches. Producer has multiple types of acknowledgement in order to make sure that producer will send the data. Producer itself contains some very sophisticated, not sophisticated, no, it contains some logic to buffer data, even like it might be failed to submit the data once. Consumer will not die. There's some retries logic, there's some buffer sizes that it can have on your client. So if the broker was not available for time being, producer will buffer some of the data, and after that it ship it when it's broker will get back up. Producer also support pipelining. You can have multiple requests per producer. So in this case, you might be losing some of the ordering guarantees, but you will have a better parallelism from one producer. And again, all these things are kind of configurable. So from your application code, you can react on this. There's a synchronous API that allows you to say so for example, if I'm looking to in my producer, when I send something to, I can define a, some like exception handler that will catch if the producer will fail. So in this case, like a failure to deliver certain message. So you can retry, you can retry and provide all sorts of logic to do that. All right. I can take the questions. I think the next speaker is here. I can take the questions out.